Welcome friends, let us talk about, we in the previous module we looked at the back propagation, the prerequisites to back propagation. In this particular module we will be looking at the learning process in back propagation neural network, and we will also be having some introduction to the other type of neural network which is also used in practice called Hopfield networks. Learning in back propagation network, we have already seen that how the Hi and Oj are calculated. 1 upon 1 plus e raised to minus some, okay. Those xi's and wi's and all that, they are multiplied and you get. So, that's how it is done. That is the first thing that we have already seen, and we know that the output is a real value between 0 and 1. The required value is either 0 or 1. Now, that is the first thing. For example, I need an output unit, second unit to be on and the rest of unit to be off, and there are 6 output units. The answer that I get is 0, 1, 0, 0, 0, 0. Okay. The second unit is 1, the rest are 0. So, that is what I want, but I may, because the output between 0 and 1, I may get something like 0.1 instead of 0, the first unit. The second unit 1, instead of that I get 0.98, and second, third one, and so on. So, I get other than 0 is values of output. Now, how that problem can be solved, or rather how to handle that, that is the first thing that we will discuss. The PowerPoint looks, you better look at the PowerPoint now. It says that the actual output that you get is 0.1, 0.01, 0.92, 0.25, 0.92, 0.87, when I actually want is 0, 0, 0, 0, 1, 1. Now, what you are supposed to do is to find out the difference. Now, what is the difference? Difference basically is the error, okay, in the absolute form, and what I want is 1 and what I get is 0.5, the error is 0.5, okay. So, that is the absolute value of error, and there is something called tolerance level as well. Remember, we have seen that in a sigmoid function case, you can't have 1 instead, unless you have the total to be equal to infinity, it is impossible for you to get 1. So, you will have to have the tolerance level. For example, we have assumed tolerance level to be 0.9. Okay. So, what does that mean? That if the difference between what is expected and what is outcome is less than 0.10, we accept it as valid input. So, that is the second point. Remember what we discussed about expected values, the values that we get between 0 and 1. The third one is the difference, and the fourth thing is the tolerance level. If the difference is less than the tolerance level, accepted, that unit is not required to be learned further, it is said to be learned. And the output unit errors are known as delta 2 conventionally, okay. The second layer weight, there are 2 layers of weight, W1 and W2, okay. Remember what we discussed about, the inputs flow in this direction, the errors flow back. First of all, the errors are available at output layer. So, at output layer we look at what is the actual value, what is the expected value, and what is the difference. So, the actual value is Oj and the expected value is Yj, then the difference is Yj minus Oj, okay. But this is an absolute value of error and we require to normalize it. So, we multiply that by Oj into 1 minus Oj. Why I am doing it I cannot explain, but accept this. So, it is Yj minus Oj, the absolute value of error, then you multiply it by Oj into 1 minus Oj. Similarly, error at Hi or hidden unit is calculated in a similar fashion. So, what does it do? Okay, we call it delta 1, the error at Hi. So, there is an error coming in from an output unit to this hidden unit, and a hidden unit contains errors coming from all output units, okay. So, basically it calculates that this way. So, this is a hidden unit, this is an output unit. So, it says that the error at this output unit multiplied by this weight, the next hidden unit, okay, the error here and the multiplied by weight, the error here and multiplied by weight. So, in this fashion it calculates, and it is shown on the screen, the W211, that W2, the second layer weight, 1, 1, the hidden layer 1, 2, the output layer 1, and error at 1, it is propagated back, okay. Same way, error at O2, and it is W2, 1, 2, okay. So, that's how it calculates W1, 3 and so on. So, it calculates that way. So, that way you calculate the error at the hidden layer. The next slide shows the formulae. So, it is sigma I equal to 1 to m, because there are total m output the hidden units. So, W2 1j multiplied by delta 2j. Now, that is the error at the hi, ith hidden unit. Okay. So, that is how it is shown. Look at two values calculated, delta 1 for the first hidden unit and delta 1 for ith unit. You can see that it is h1 into 1 minus h1 or hi into 1 minus hi, that is for normalizing the error. Okay. The absolute value of error is normalized by multiplying this. And you can see that the summation is also the same, the hidden unit, output units, the error here and weight, error here and weight, error here and weight. The multiplication and those multiplications are summed up. And when we are looking at this, remember we had a problem of negative and positive misclassification. So, negative misclassification you will have to increase weights, positive misclassification you will have to reduce weights, and that is you have to calculate weights that way. Interestingly, Oj into 1 minus Oj or Hj into 1 minus Hj is always negative, because one of them is positive, the other one will become negative. Okay, so that is always negative. So, that is one thing. So, error, if you just add that thing, multiply that thing, it negates everything. For example, Yj is more than Oj. Okay, Yj minus Oj is positive. When you multiply with Oj and minus Oj, it becomes negative. Similarly, if it is negative, Yj is less than Oj, the multiplication, the value becomes positive, the error is high, and that you can just add. Okay, so you don't need to process it further, you will just add that, because the sign is taken care of. Okay. The W211 error is based on H1 and O1, W211, H1 and O1, W212 is H1 and O2, and so on. Okay. If you want to update this weight W211, okay, so that is here the output unit W2ij, jth output unit, ith hidden unit. Okay. So, that is the weight between the W2ij is a weight between ith hidden unit and jth output unit. Okay. So, if you want to update that weight, that depends on H1 that is coming in, the value that is coming in, and the error that is coming from this side. Okay. So, that is something that you will have to change. Okay. That is going to have an effect. So we have this multiplication hi into delta 2j, ith hidden unit, jth output unit. Remember this, they are not same, I and j are different. So, if I want to update that weight, the formula is shown on the screen, delta, that difference is known as delta W2ij. So, that is hi into delta 2j, and that is also multiplied by a value called eta, that is 0.35. People found that if you use this, it learns better. Okay. So, that people use, the researchers use. Sometimes, and many a times it is kept in some other values also, but usually it is between 0.3 and 0.4. Similarly, W2ij, the new value of that weight obviously is the old weight plus this delta value, the change that we want, plus that delta. Okay. And people have also, researchers have also found that by just simply adding this, the network will definitely learn, but will learn bit slowly. So, what you can do is, in the initial run you let the weight gets updated that way, but later on you multiply that with a value called alpha, which is quite near to 1, 0.9 or something. So, when that is multiplied, the speed of learning improves. The same thing happens in W2ij as well. Almost the similar set of calculations are made. You can look at the PPT or the handout to see that thing. There is no difference almost. Okay. The only issue is that the second layer of weights we call them W2ij, and the first layer we call W1ij. Some other authors have chosen some other mechanism. Some of them use that suffix at the end, some of them use that suffix in the beginning, but otherwise basically it is the same. And that alpha, that value something near to 9, is called momentum factor. As I said, it improves the speed of learning, and that is why it is called momentum factor. Once these weight updates are applied, one epoch is said to be over. Now, remember, let me recap what we have done. You find an error at the output unit, Yj minus Oj. normalize that by multiplying it by Oj and 1 minus Oj. So you have found that for all output units, find these errors. Once that is found, you calculate errors at HIs. HI is basically a summation of connection. Okay, it is connected to all output units. For every weight you need to look at that. So for this particular weight, it is HI and Oj. We have also calculated the error. The error is delta J, that is this error, the jth unit or the first output unit, the second output unit, third output unit, and there is a weight. Okay, so you calculate this error at the output unit, multiply with the weight. Okay, you get that error at HI. And how you calculate the update the weights? Okay, you just say that this is the error, and you calculate that. And now error is to be added. Remember that the original value is negated. So you are just adding an error, you are improving it, you are improving the weights. So once you do that, your weight becomes more aligned with the input. Okay. So that is what we have seen. So that now we are going to look at that complete algorithm in single shot. So these are the building blocks for that algorithm. Okay. So once you apply input, calculate weights, update all weights, you apply the next input, and it is a huge thing. For example, we have 50 employees and every employee 20 images. It's 15 to 20. 1000 total inputs are provided. For each output, you check whether the output is right or wrong, and for every wrong output, you will have to update weights. Okay, so once the whole thing is done, one epoch is said to be over. And when one epoch is said to be over, only the first phase of the problem is solved. The second phase, you redo it. In fact, you require many epochs. In some cases, you require 25,000, 30,000 epochs. This is a typical case of signature recognition system which some of my students worked at. So it minimum requires 25,000 to 30,000 inputs. And if the input is more complex, number of input units are more, number of output units are more, you probably need huge number of iterations, sometimes even going beyond 1 lakh or 2 lakh sometimes. The only catch is that sometimes you won't get it learning. So after some reasonable period of time, reasonable number of iterations, if you find that is not learning, there are two ways of finding it out. One, look at the difference between error. So if the weights are not actually updated, just going is oscillating, for example, adding something, subtracting something, adding something, subtracting something, then you understand that is kind of a local minima or maxima you stuck with. So that is one measure of doing it. Second is it takes inordinate time to learn. Okay, normally if it learns in 2 minutes or 3 minutes and it takes 1 hour, sure that there is something wrong. What is the solution? There is no complicated solution in this problem. What you are supposed to do is you just rerun that program. That's all. As I said, if you rerun that program, all W1 ijs and W2 ijs are picked up randomly. When they are picked up randomly, they represent a random node on that n-dimensional space and a different starting point for us. And it's quite possible that using a different starting point, you won't indulge into that local minima or maximum problem, and you will reach. Practically, it is found that in most cases, you sometimes you require to rerun, but most cases it will reach there without much of an issue. You may ask the next question, what is the guarantee that we will get that weight vector? We will learn everything, every input. You provided all 50 images of employee, and what is the guarantee that the program will eventually learn, identify each employee correctly? Theoretically, there is no guarantee. We cannot. The backpropagation algorithm that we are using does not guarantee anything here. It doesn't say that it will surely find out, I guarantee that. Okay, so there is no guarantee as such. But as I said, practically in most cases, it does. Okay, the errors coming at H1 is depicted in the figure that is there in the handout as well as on the PPT. You can see that there are 3 layers of the multi-layer network, the XIs, the HIs and the OJs. Okay, you can see that H1, connection of H1 with O1 to OL, all of them. Okay, and you can see that W2 11, W2 12, W2 13, and all of them are actually calculated. Now you multiply the errors okay, that you get at O1, O2, O3 with the respective weight, and that error is calculated at H1. This figure clearly indicates how that is done. And this is just one example. The same way you calculate errors at H2, H3, H4 and so on. Once those errors are calculated, the weights are updated. We have already seen how the weights are updated. Now let us look at the algorithm in a single shot, as I have already mentioned. It's very complicated algorithm on the face of it, but otherwise it's not all that complicated. If you look at this, you will realize. Okay, first thing is to decide number of neurons at each layer. You will have to decide that, and how it is done we have already seen a few times. You decide input based on the size of file, output based on number of classification classes that you would like to classify the inputs into, and the hidden units as geometric mean. Sometimes the hidden units are taken little more than geometric mean when the number of features are more. Remember, the job of hidden unit is to identify features out of input. So if you believe that the features are more, the number of hidden units are increased. And if you believe that number of features are less, depending on the problem that you are solving, they are reduced. Okay. So as I said, this is all empirical. People have done a lot of work on it and a lot of research on it, and the results contain a lot of guidelines for people like us who would like to code. And now you randomly initialize both layer of weights between 0.1 and minus 0.1, or sometimes even minus 0.05 and plus 0.05. Now, why we are keeping this weight value as very less? It's because researchers have again found that if you start with very less value of weights, the network learns quite easily. But if you keep some weights large, the problem is that those weights will bully others into that direction. So network will not only misclassify those bulky weights, will drive the network to learn in something different than what we want it to. So the good idea is to keep the random weights that we start with to a very low value, which is indicated here. And that's going to be, we begin with our epoch as 1. So that is epoch as 1. And now you pick up the first input. For that input, obviously all I values you just provide to xi's, and you let the hi being calculated. You know how it is calculated. OJ are also calculated. Find errors. Okay, how you find errors? You'll have to get correct value for output units. So they are called yj's. So get yj's, find delta 2, the error at output unit, find delta 1, the error at the hidden unit. If this weight is to be learned, please understand, if it is correctly identifying, for example, I want that output unit to have value 1 and it gets me 0.98 and my tolerance level is 0.1. So it is fine. It is anything beyond 0.9 is acceptable to me. So this unit does not require to learn. So I will not do anything here. But if it is 0.6 or 0.7 or 0.8 or 0.85, I know there is a difference which I want to bridge. So in that case, this process is applied. Okay. The weight is updated. Okay, so that weight update process, which also uses eta as well as alpha, as we have seen before. And once you do that, first of all you decide the W2 ij and then W1 ij, and then update the weight by old weight plus this delta, okay, and old weight plus alpha into delta, and so on and so forth, which we have already seen. So I am not going to stress it further here. Now this is something to be done for a single input. Once this input is done, you will try the next input and the next and the next and so on till all inputs are done. When all inputs are done, the weights are updated, one epoch is said to be over. So the epoch value is incremented by 1. And if all units have learned everything, you stop. If it is not, you start with the next epoch. Okay, so you go back to the place and restart. Okay, so the algorithm have to restart from that place. Again, take the first input, second input, third input, update weights, update weights, update weights. And at the end, if it finds that, okay, there is a unit which is not learned, and will again restart. So it will continue till all units are learned. That means that the expected value and the value that you get, the difference between them is less than the tolerance value. For all units, if it is the case, the neural network is said to have learned what we want it to. Once that is done, what we do is we store this weight W1 ij is basically a matrix. W2 ij is also a matrix. So this matrix value is stored somewhere. Why? Because whenever we are testing this neural network, we will provide this information. Now we are not going to change these weights. We just let it flow and we see what the output is. So that is called testing. Now the testing also, you need an algorithm. So how? Well, then the algorithm, the handout and the PPT contains that algorithm as well. The algorithm begins with simple. Okay, the same backpropagation neural network setup is provided. But instead of providing random weight values, you just populate it by the weight matrix that we already have stored. Now you provide the first testing input, let it flow, and the output is generated, that output is recorded. Output is not, you don't flow the errors back, you don't do anything, you just note the output. And it is quite possible that you test the input for 20 test cases, and out of that 18 you get the correct answer, 2 you may not. That is perfectly acceptable. It happens, and that is common also. It's the same way with child. When you provide child with some examples of A and some examples of B and so on and so forth, sometimes he mistakes I for H and H for I. It is possible. So that is common. That is like human. Okay. So that is what is done. Usually the tolerance level for testing is much higher. Okay. So in most cases it is 0.5. So if it is more than 0.5, it is considered to be 1. Less than 0.5, it is considered to be 0. So tolerance level is high. Obviously, it has to be high because program has not seen this input. How actually this learning process is doing it? What is the mathematical view of it? If you want to understand, you can assume that we only have a 2-dimensional space. Remember, we need an n-dimensional space if we are using n weights. There is a figure in the handout as well as the PPT which talks about a 2-dimensional space. In a 2-dimensional space, we have multiple regions defining a class. What we want to do is to have and we take a very simple case where there are only 2 types of inputs, A and not A, for example. And what we want is to have a line which separates them. So that line will have some slope and a C value, y is equal to mx plus c is the equation of line. M and C are constants and they are decided by this weights that we provide. So when we start with random weights, the line actually is drawn in a random way on that plane. So when we continuously update that, basically you get a line which separates what we want. So A and not A can be separated. If you have A, B, C, what we need is there are multiple classes, so we need multiple lines, and for that we need multiple neurons. So once you do that, once the lines are properly drawn, the figure actually talks about a case where there are 1, 2, 3, 4 lines which are drawn in a way that it can separate 1, 2, 3, 4, 5 different classes. So if you get those lines right, it will be able to identify. Okay. So basically the learning process is moving off that line to its right position which can separate the regions which describe a class. This line is known as decision surface, and if in a 2-dimensional space is going to be a line, in a 3-dimensional case is going to be a plane, and so on. It can be n-dimensional plane, you have an n-1 dimensional decision surface, and that decision surface, the learning process is basically to start with a random decision surface and come to the right or correct decision surface, move in a direction to get one decision surface. But then there is one more thing which we must understand, that not always you have one decision surface. There are potentially infinite number of decision surfaces. We need to just get one. Okay. So in most cases we'll get one and our problem is solved. Finding out correct planes, as I said, is a process which begins with random values, okay, and converges to the right set of weights. The next thing that we are going to look at in this particular module is called Hopfield networks. We only would trace a point here that the same thing which was used for localized information storage, you can use for distributed storage. For example, if you have 8 units, you can use 8 units to store 2 raised to 8 information. But here you can use them, and there is an example shown in the handout as well as the PPT, a simple Hopfield network. You can see that there are 8 units and they are connected with each other using some weights. Now once you connect them using some weights, what do they do? In fact, every unit does something that we have already seen. Every unit calculates the input multiplied by weight. If the input is 1, the weight matters. If the input is 0, obviously the multiplication is 0, so the weight doesn't matter. So what does every unit do? Every unit will look at the summation. If the summation is positive, it will learn to become active, that means it's 1. Summation is negative, it will be 0. And every unit, if it's connected to some other unit with positive value, it says to be stimulus. It provides that stimulus for the other unit to remain on. And it provided negative connectivity. If the weight is negative, it inhibits that neuron. Okay. So here you can see that there is a connection between the first unit and the fourth unit with value 5. What does that mean? If the unit number 1 remains active, it tries forces the fourth unit to be active at that weight 5. It is also possible that a unit contains some negative, some positive values. At that point of time, the summation is done. Let us start, and again it's quite interesting. Such a network will only have few stable states. For example, let us begin with this case where we initialize the first unit with 1. The rest of the units are not touched, but you can see that it is connected with the third unit in a negative connection, the fourth unit with positive. So if you set the first unit to 1, the third unit becomes 0 and the fourth unit becomes 1 automatically, because they are connected that way. When you make the second unit turn on, you can see that the next unit, the 2 more units, 6 and 7 units will get 0 and 1 because they are connected that way. So you just do that, is the process is shown in the slide, that you just set a few values and you get the answer. And if you change them, you set first 2 and the last one, you get a different answer. In fact, there are few different answers possible, but only few of them. In this case, I believe that there are 3-4 possible answers. You start with anything, you get either of them at the end. Now you may tell me that suppose if it gets 5 or 6 total possible values stored. Now in the earlier case I had 2 raised to 8 and now I only get 4 or 5. What's the advantage of doing it? The advantage of doing it is that this mimics human capability of associative search. So this, for even incorrect inputs, you will be able to get the right output. Okay, so that's the power of Hopfield network. In fact, with Hopfield network, there are a lot of other things which one can talk about. I won't be talking about them. One big problem which this thing Hopfield network can solve is traveling salesman problem. Okay, with that note, there is some information available about this thing in our handout, and as well as a lot of other references which talk about that. With that note, I'd like to conclude this thing and just summarize everything that we have done in this module. We looked at how backpropagation calculates the activation, changes the weights, updates itself, and get the right set of weights for every input to be classified properly. We also seen how Hopfield networks are used for associative search. With that, we'll conclude. Thank you.